Hello everyone. Let's look into few of the rules that we need to follow while doing a proper routing. So it's called design rule check. It's the short form is DRC. So while we do it, we what we'll do, we'll take some example of we'll take some handful of examples of DRC and try to see how do we do it. So for example, you let's say this particular section of the circuitry, you have these two wires which has being just expanded over here. So the rule says that whenever you try to build two wires, there should be a minimum distance between these two wires and there should be minimum spacing and all those things. So let's try to look into few handful of rules while trying to route these two wires. For example, we are trying to connect this buffer with this buffer and this flip-flop with this logic gate 1. So while doing that, we see some parallel routes and there should be certain rules that we should be following while doing while following any kind of routing algorithms. Okay, so let's try to look into few of them. So for example, the three basic rules for this below pair of wires will be the minimum width of the wire should be some X number. So this is the minimum wire width, and the rule says that the width of this particular wire should be some at least this much. It can be greater than this much, but it should be at least this amount. So what it says is basically there are some techniques to build these wires, and those techniques are referred to as photolithography, optical photolithography techniques. And these techniques use light to build these wires, and light has got certain minimum wavelength, and with that particular wavelength it can draw a certain minimum width of the wire. Okay, so considering that into mind, we come up with this certain rules, and the rules say that the optical wavelength of the light is so small that the wire width, the minimum width of the wire should be at least this much. You can't go below this one because it can't be printed. Okay, that's what the rule says. It's basically mostly related to the optical lithography techniques, and we will be talking a lot about optical lithography in a separate videos, in a separate section, where the lithography as well as the DRC rules will be in junction with each other. They will be in par, they will be going hand in hand. Okay, in this case, let's try to understand a light. This all wires that you see that are built with the help of some light, and light has got certain wavelength, and that wavelength of light can build a wire with certain minimum width. Okay, it needs, the wire width will be at least this much. It can exceed this particular wire width, and in most of the cases it does exceed. Basically, the shape that you see of the wire over here, it's not always rectangle. Once it comes after lithography, there will be some vibrations over here. Okay, so those things we'll be talking in a separate set, but right now the optical wavelength of the wire says us that at least the wire width should be this much. It can be more than this, but it can't be less than this. Okay, there's another rule that the lithography thing tells to us, is that the minimum pitch between two wires should be this much. It basically says that the center to center distance of these two wires should be at least this much. So these things comes after a lot of optimization done on the lithography system. So there are multiple lines that are getting printed. So how do they come up with this wire pitch? So they print multiple lines with varying pitches, starting from closest to the widest, and then they come with an optimum numbers. For example, this one, which will be printed very faithfully. So what you see on the mask is what you see on the silicon. That's how they come up with this particular numbers. Okay, and we'll be talking about more of optimization on lithography techniques in a separate set. Let's try to focus on the concepts over here. So this is how they come up with this minimum wire pitch and minimum wire spacing. Okay, there is a third rule. There is one more rule that below two pair of wires has to follow, and that is the wire spacing. So it says that minimum spacing between these two wires should be at least this much. It can't be less than this. It can be more than this, but it can't be less than this, because it won't be getting printed on a silicon as per the optical lithography rules. Okay, so these were some few basic DRC rules, and there are tens, thousands of rules that the router need to take care while routing between two logic cells. While routing all these nets, the router has to, or the routing algorithm has to be aware of at least 1,000 rules. We have just mentioned three of it. Okay, and this will be more clear and more sensible when we try to match this with some lithography courses. So let's try to keep it over there. Let's look into another section. For example, let's say we have this section. This section has got there has got two nets. One is this one, which is an orthogonal net, and one is the straight net that is going above it. So the basic problem that you see with this net is that they are shorting. So there is a signal short over here. So this flip-flop is communicating with this particular logic cell, and this buffer is communicating with this flip-flop. In the process, if you see, when this buffer tries to send a signal to flip-flop 2, it gets shorted with this signal because both are same wires and on the same metal layer. So we need to take care of this kind of situation, and this particular situation is referred to as signal shorts, because your signals are getting disturbed over here, and that's a potential violation in a VLSI world. Okay. So these things might lead to functionality failure and so on. So these are very serious things that we need to be looking for. So the signal short is one of the rules. Apart from that, the remaining three rules will be still maintained between these two wires: the wire width, the wire spacing, and the wire pitch. So let's quickly see how do we solve the problem of signal short. What we do is we take this particular layer, or we take any of the layer and put it on a second layer. For example, let's say this colored wire is referred to as metal layer MN, and N is either 1, 2 something. So we take another layer which is MN plus 1, which is metal layer N plus 1. For example, if this was metal 2, let's say, for example, if this was metal 2, there will be one more layer that will be introduced at the top of it. It will be called as metal. If this is metal 2, this will be called as metal 3. Okay, usually the upper metals are wider than the lower metals. We have not shown it over here, but from a DRC point of view, or from a signal integrity point of view, you have the upper metal layers wider than the lower metal layers. Okay, while we use this technique to solve the signal short problem, there are few more DRC rules that come into picture. For example, let's look into few of them. So this, we have solved the problem of signal short, but we have increased the number of DRC check, something like this. So you have two new DRC rules that needs to be checked. One is the via width. So you need to connect the bottom metal layer to the top metal layer, and that you will be doing through with the help of a wire. It's like a screw that you try to connect between two different things. Okay, so this is the via, and the rule specifies that the via width should be some minimum value. It can't go below this, but it can be more than this. But for a via which is something like this, it specifies the via width should be some number, and it can't be less than this. And this again related to the optical lithography technique. So most of the rules that comes, of all of the rules that comes, the design rule checks that comes from the optical lithography point of view, the lithography techniques point of view. So it's very important to understand what lithography technique is, and how do these numbers are extracted from the lithography experiments that we do. Okay, so based on the lithography experiments, so one of the experiments that we can share it right over here is they print the square boxes that you see. They print these square boxes multiple times at varying widths, and then they come up with a width saying that this is the minimum width that can be printed by an optical light. Okay, and there is one more rule that comes, is the wire spacing. So minimum spacing between these two wires should be at least this much. It can be more than it, but it can't be less than this, else it can't be printed. Okay, so it's more of a printing. How do we print what we see on the layout, and that's what a layout term comes into picture. So this has to be laid out onto a silicon, and that is done using lithography techniques, and those techniques come up with some rules with which the algorithm, the routing algorithm, needs to follow. Okay, so we have covered the DRC technique in brief, and there are like tons of DRCs that we need to learn and understand, and that will be binded with the lithography lectures that will be uploading in some time from now. The next step is to is called as parasitic extraction. So basically, whatever wires you see over here, these wires are nothing but some physical wires. They have got certain width and height, and the resistance and capacitance of this particular wires needs to be extracted and to be used for some purpose, something like this. So if you see the resistance and capacitances on this particular wire, each and every wire has got some finite value of resistance and capacitance, and this needs to be extracted and used for further process. Okay, so since I'm already running out of time, what we'll do, we'll see how do we extract the parasitic. We'll look into certain formats, it's called SPEF format, standard parasitic extraction format. It's an IEEE format. We'll be deep diving into the SPEF format and trying to look how can we represent the resistance and capacitance of a net in a different file. So let's try to look into all those in the next video. Thank you.